Okay, great. Yeah, first thing I want to do is I'm just going to take a screenshot here. Sometimes it doesn't want to go all the way. There we go. So like we were just saying here, let me highlight without moving the screenshot. We do have quiz number 2, which is on chapters 3 and 4, okay, which is going to translate to assignments 5, 6, 7, and 8. 8 I have not posted yet, but I will, which is going to be on the normal distribution and the binomial. Unless I take those questions and I split them up, it might be 2, but it'll be the same number of questions, so it doesn't really matter. But use these questions for practice. Okay, so I'm not gonna stray. These will be the questions, just different numbers, right? So as long as you're comfortable with those, then you'll be all good. Okay. Oh, I must not have refreshed. I did fix it. So last day we finished the normal distribution. We're going to parking lot that. We are going to come back to the normal distribution. But today I want to skip ahead to the binomial. So I'm going to parking lot the geometric distribution, kind of lump it in with the less important distributions, which we'll talk about on Thursday. Less important. We'll spend a little bit more time on them in Stat 240 if you're coming with me to Stat 240. If not, they're not terribly important. I will say that this quiz, chapters 3 and 4, in my opinion, will be the hardest quiz. Okay, there's a lot of material, right? We talked about probability, and then we talked about the normal distribution, which is kind of completely different, it feels like. And then today we'll introduce the binomial distribution. So there's material from all these angles. And so it's kind of, in my opinion, this is the hardest quiz because there's kind of so much to keep track of. Okay. But once we're over this quiz, then we'll be kind of on easy street, in my opinion. It won't be for you because you don't know where we're headed. But for me, right, we get to kind of slow down and really kind of focus on stuff after this, after chapters 3 and 4. So same idea for the quiz, right? For quiz 2, you're going to bring your laptop in and you're going to do the quiz. I'll give you scrap paper for you to do any calculations, especially for things like the binomial. If you kind of mess up a number, it'll really kind of translate. So I do want to be able to check your work or whatever you give me, right? It doesn't have to be fancy or anything, but I do look through it just to make sure that it's not just a typo, right? I don't want you to be penalized for that. Okay, let's see here. So just in terms of review, like I said, we're not going to use the normal distribution again until next day. So let's just say that the normal distribution it models continuous data. So there are distributions that model continuous data, and then there are distributions that model discrete data, so counts, which is what we're going to talk about today. All right, so let's just make a note here. It models continuous data. And now I'm using data instead of variables. But you can kind of use them interchangeably. And we know for normal distribution, well, we had to have numerical data. So today, it's not much of a review, but today we're going to introduce the binomial distribution. We will introduce, the binomial distribution. And like I said, the binomial distribution models discrete data. It models counts, let's say that, which are discrete data / variables, which are still numerical, right? Any counts are numerical, but they're discrete. So binomial distribution, so we've got these two main ones that we introduce in this course. And depending on the scenario, right, you would have either a normal distribution. Okay, so then I tell you this follows a normal distribution with a mean of this and a standard deviation of this. And that tells you, okay, I need to follow, I need to calculate a Z, and then I use the Z table to find probabilities, right, that kind of thing. Or now we're going to be able to identify a binomial situation. So first we need to know what that is. Okay. If you want to be kind of really elementary about it, right? If you're looking at a screw, for example, and you want to figure out how to screw it in, right? You would use a screwdriver and not a hammer, right? So that's kind of the same idea for, okay, I've got a normal distribution, so then I apply these methods. Okay, now I've got counts and it satisfies this binomial situation. So then I apply these methods, right? So section 4.3 is the binomial distribution. So a binomial situation, and I will say we will save 4.2, which is the geometric distribution. So it's another scenario, but it's not as prominent as the binomial. So we'll save 4.2 for next day. All right, so I am like the rare times that I skip around 4.3 first. So a binomial situation is when the following are satisfied. And let's talk about that. So is when the following are satisfied. So a binomial situation, clean that up. First thing is that there are only two possible outcomes. Okay. So we boil it down to a success-failure situation, right? So there are only two possible outcomes. Only two possible outcomes. Which we usually talk about success-failure, which could be something like yes, no. That's really common, right? They clicked on your ad, they didn't click on your ad, right? So yes, yes, no. Usually we call it a 0-1 situation, but in keeping with kind of the success, yes, right? Those would be ones and everything else would be coded as 0. So 1-0 or 0-1 situation, which we generically call a binary outcome at 0-1. Yeah. Even situations that are not explicitly binary, right? So not explicitly success failure. If I roll a 6-sided die, right, there are 6 possible outcomes, but if I'm only interested in rolling a 1, right, I would call that a success, and then all the other ones are failures, right? So we can make binary situations if we have to. Okay. And it's a little bit confusing because the success is often, so the success is the thing that we're interested in, right? And the thing that we're interested in is not usually like a yay, success. It's usually, oh, this many people died from this vaccine, or this many people died from this disease. It's usually pretty morbid stuff, right? So it's whatever we're interested in, right? But of course, that's what we would be interested in if we were studying a disease, for example, right? Then we want to follow the people who die from a disease or that kind of thing, have side effects, right? So it's usually a bad thing, but it's the thing that we're interested in, right? So the success is the outcome we are interested in. Yeah. It gets a little bit confusing because even within the same question, right, the outcome that you're interested in can change, right? So just kind of be aware of that, thinking of one problem in particular. Okay. So you only have 2 possible outcomes. Okay. Yes, no, success, failure. The second criteria is that the outcomes or the trials, we're going to start calling them trials, have to be independent of each other, right? And we remember, oh, independence, that's from probability. That means that the probability of one thing is not affected by the outcome of another thing, right? So the probability of success stays the same is what that's saying, right? So the outcomes, which I'll write up here, we're going to start calling them trials. So the trials must be independent of each other. Must be independent of each other. Right? And knowing about independence, okay, what's that actually saying? It means the probability of success is the same for each trial. So therefore, the probability of success is the same for each trial. Okay. Flipping a coin, for example, we know that's an independent random process because flipping a coin, it doesn't matter how many heads I've seen already, the probability that I flip a coin and I flip it to heads again, right, is still 0.5, right? And so I don't know when I started using this example because I'm not a sporty person, as in I don't do any sports. But I'm shooting hoops. No, I stole this from a textbook and they were trying to be all cool. You're shooting hoops and the probability that you get something in the net, right, let's say is 0.2 for me. That's probably a little high. Probably more like 0.01, but that's okay, right? So I'll lay out the scenario and then we're going to talk about why it's a binary situation, right? And then I want to show you that you actually have the tools to solve this problem already, right? But it's going to get pretty clunky pretty quickly, and I'll show you why. But let's write out this example first. So for example, I'm shooting hoops. Which I don't even really know how to do, but gym class for me was just being hit in the face with whatever sport we were playing, volleyball, basketball, doesn't matter. I'm shooting hoops, and the probability of getting a ball in, I guess in the net, feels like hockey, but whatever, is 0.2. And each trial is independent of the previous trial. And each trial is independent of the previous trial. I know you could argue that if I've done it, 20 times, you'd think I would get better, but I know I won't. So they're independent. Let's say for this example that we're going to solve, right? If I try to shoot it 5 times, what's the probability that it goes in exactly twice? So I shoot 5 times. What is the probability that exactly 2 go in? So this is kind of a typical problem, or at least one that we're going to start with. So first thing I want to do is I see no mention of a normal distribution, and I see no mean or standard deviation. So I know it's not a Z-score question. So kind of by elimination, I can say, okay, it's not that path, right? So then I'll start asking myself, okay, is it a binomial situation? So let's go through and see if it's a binomial situation. So is this a binomial situation? First criteria was that there's only 2 possible outcomes, which there are, right? It either goes in or it doesn't, right? Only 2 possible outcomes. Right, either goes in or doesn't. Right, success, failure. And then the second criteria is that the outcomes or the trials must be independent of each other. Right, the probability of it going in stays the same for each trial. And so that's true. Trials are independent, which means, right, the probability of success is always 0.2. Okay. So if I let S generically denote a success, right? Just so I have some notation here, let S just denote a success, because that way you can apply it to a different scenario, right? So let S be a success, which in this case is getting a ball in, which means the complement of S is a failure, which is missing. We could, like I said, you have the tools to solve this problem, right? How? We could use a tree diagram, right? I shoot once, it either goes in or it doesn't. And then I shoot another time, it either goes in or it doesn't. Or if it didn't go in, it either goes in or it doesn't, right? And then with 5 times, right, I've got 5 layers of my tree. I am going to draw it out, and it is insane. So buckle up. Here we go. So I will say that we could solve this problem with a tree diagram, right? And we will, just to show you. But what you're going to find, right, is that this gets really clunky really fast. And you're not going to want to do this, but I'm going to use this to help build the formula that we're going to be able to use. So there will be a quicker way to do it, right? But just so you have that connection that you could solve this problem using a tree diagram. Oops. I've got a page breakdown here. So let me just 1, 2, 3. Okay. I guess I'll need to put it on a fresh page. Or I guess I could draw it on this fresh page and then shrink it and move it up. Okay. You'll see why you need a lot of space, right? Because each of the branches, right, are going to result in 2 of their own branches, right? And so if we start here, I'm going to give myself lots of space at the top, right? This is trial number 1. Right, first time I shoot, it's either a success or it isn't, right? Kind of generically. And the probability of success is 0.2, which means the probability of not a success is 0.8. So if it went in on the first try, then I guess I kind of cramped up here already. Right, it either goes in or it doesn't, and the probabilities stay the same. That's nice, right? Because the tree diagrams that we've used have had conditional probabilities, right? So depending on what your first branch was, right, then that'll tell you the probability of the next few branches. But here they're independent, so we can just go for it. So then even if it didn't go in on the first try, that's okay. It could go in on the second one or not, all with the same probabilities here. So this is trial number 2. I was shooting 5 times, right? So, so far I've done 2. So now I'm gonna get really lazy and I'm gonna start just attaching upside down V's to all of these, right? But this pattern is going to be the same, right? S, not S, S, not S. So it's going to look like this. So that's trial number 2, or sorry, number 3. Number 4. And then finally, number 5. I have to be careful that I don't start drawing A's. There. Right. You're probably not going to want to do this, right? But I just want to show you that you do know how to solve this problem, right? It's just tedious. Okay. So what we would do, right, is we would trace our way down these branches, right? And we would say, okay, well, if the first one goes in, let's remind ourselves that we're looking for the probability. So I shoot 5 times. So we've mapped that out, all the possible outcomes, right? What's the probability that exactly 2 go in? Okay, so now I'm going to methodically work my way through each of these branches. And I'm going to start with the first one going in, right? And then if I force the second one to go in, then there are no more options, right? It has to be exactly 2. So then none of the rest can go in, right? And then because it gets pretty crowded down here, I'm just going to highlight that that was one of the branches where exactly 2 out of 5 go in, right? But knowing how the branches work, right, you know that there are other options. So now let's go through and say that, okay, the first one goes in, the second one doesn't, and then I like to kind of force the third one to go in because then the rest don't, right? So that's another option where it goes in or where it satisfies that criteria. If the first one goes in and the second one doesn't, and then I force the third one to not go in, I can force the fourth one to go in. You can see it gets pretty overlappy, which means the fifth one cannot go in. Same idea. If the first one goes in and the second one doesn't and the third one doesn't and the fourth one doesn't, then the fifth one has to go in. Notice that if you were multiplying down these branches, right? Because at the end of each of these branches, you're multiplying, right? 0.2 times 0.2 times 0.8 times 0.8 times 0.8, but the order doesn't matter, right? And so we're gonna leverage that, right? Because we're just multiplying different combinations. Really what we're after is how many combinations do we have here, right? Okay, so I'm done with this success first branch. So what if the first one doesn't go in? We do the same thing. So the first one doesn't go in, and then I'm gonna force the second one to go in. I'll also force the third one to go in, which means that the next 2 cannot go in. Well, same idea. The first one does not go in. The second one goes in. I'm going to force the third one to not go in. Fourth one goes in, which means the fifth one cannot go in. And I've got another option down this branch. First one does not go in, second one goes in, third one does not go in, fourth one does not go in, which means the fifth one must go in. Yikes. We're almost there. First one doesn't go in, second one doesn't go in. I'm going to force the third one to go in and the fourth one to go in, which means the fifth one cannot go in. Same idea. Doesn't, does go in, does not go in, does go in. And then finally, first one doesn't go in, second one doesn't go in, third one doesn't go in. My only option here is that the fourth one and the fifth one go in. Hopefully I got them all. Let's count how many satisfy the exactly 2 successes criteria. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got them all. How do I know? Oh, the choose function. So, and we'll talk about that. But so here we see that there are 10 different ways to have exactly 2 successes in 5 trials. So here we see there are 10 ways to have exactly 2 successes in 5 trials. Okay. But like I was saying, right, the probability, how we find the probability at the end of each of these branches is the same, right? We have 2 successes and 3 failures, right? So here, since we are multiplying down each branch, right? The order doesn't matter. So since we are multiplying down each branch, the probability at the end of each branch will be the same, right? Since order doesn't matter. The probability at the end of each branch will be the same since order doesn't matter. Right, so it's going to be 0.2, right? The probability of success. Let's use green instead. 0.2 is the probability of success to the power of 2, which is the number of successes times, and I'm going to use brackets here, times 0.8, which is the probability of failure, to the power of 3, right, which is the number of failures. So what we decided using this tree, right, is that, okay, I know how to find the probabilities at the end of each branch. And so now I could say, okay, well, exactly 2 successes happens down this branch or this branch or this branch or this branch, right? So 10 different ways. So then what we would say is, okay, to get that total probability, I would multiply this by 10, right? The number of ways that I could have exactly 2 successes in 5 trials. So here, I would say 10 times this, or maybe I would write it in blue and then I'll highlight 10. And this 10 is the number of ways to have exactly 2 successes in 5 trials. Of course, I have to have my panicky moment. Great. Okay. So this is where the formula that we're going to be able to use comes from, right? And so if you want to think about a tree, then that might be helpful, right? But if I say, okay, now I'm going to shoot it 20 times or something like that, right? Even 5, I think, is too many to draw out in a tree, right? But now let's push it. Let's say I do it 20 times. That tree would be insane, right? And so instead of tracing out manually how many ways, right? This is the hard part, finding this number here, right? How many ways can I have exactly 2 successes in 5 trials? And so that's why we're going to use the choose function. I call it the choose function. Okay. And so let's see here. We can find the number of ways, right, to have k successes in 5 or in n trials. We can find the number of ways to have, and I use a lowercase k successes in n trials, right? So in general, right? Using the choose function. The choose function. I'm pretty sure it's not called the choose function, right? It's the number of combinations, but I just find that it helps if I call it the choose function, because then you can say, okay, how many ways can I choose 2 in 5 trials, right? And so we write the choose function, usually something like this, n choose k, or a lot of calculators, including my own, uses NCR. Or we will use this notation, which is a big bracket, n choose k. Notice that this is not a fraction, right? This is the notation that we use, n choose k, right? So this reads n choose k. So it's not a fraction, right? You want to be really careful that you don't do that, right? And I want to show you how to use the choose function. I'm going to use the Desmos. You guys familiar with Desmos? Usually use it for graphing. It's a free app. It's this one here. This is the graphing one. But then if you Google Desmos Scientific, or just in your app store or whatever, it's free. So I'm going to use that just to show you. But I'm pretty sure even if I use a different calculator, this one has ads and it doesn't like being like this, likes being like this, but it has a choose function, right? So wait. There, right? So all calculators, any scientific calculator will have a choose function, but I'm going to use the Desmos one because it's a little bit fancier, a little bit cleaner. Okay. So this is the Desmos scientific calculator, and you'll have all the similar functions on your calculator.
Can we use this for the exam?
Yes. Yeah, you can use Desmos calculator for the exam if you want. Yeah, make sure that whatever calculator you're using, right, you can't use your phone, but you can have it set up on your computer. Okay. This is one of those times, one of those quizzes where using one of my random calculators for the first time is not fun. It's never fun. So you want to make sure that you're prepared with your own calculator. I'll bring them, but yikes. So here there's a function tab, and in that function tab, if I go there, there's this NCR button. If you're familiar with factorials, right, we could use factorials instead. I'm kind of cheating. We're not talking about factorials, but NCR. So if you hit that NCR button, and if you're on a different calculator, sometimes it needs the N first, and then the NCR button, and then the R button. But if I wanted to know how many ways, or confirm that there are exactly 10 ways to have 2 successes in 5 trials, how would I write that? I'd have to say, okay, in 5 trials, and then comma 2, and then end bracket. Down here, it shows the answer. So I'm going to screenshot this and bring it in. And I do want to have that in there as well. Oh. I got 10. Right, so here, this 10 is 5 choose 2, right? N choose K. So we found that 5 choose 2 equals 10, which we can confirm. And this, I'll just make a note here that this is the Desmos scientific calculator, in case you're interested. So we'll do a couple of choose functions just so you can make sure that it's working with your calculator, so you know how your calculator works, right? But here, right, this is the NCR button, the N choose R button, and then the answer is 10, right? 5 choose 2. So if we know the number of trials and we have how many successes we're interested in, right? And also we need to know the probability of success, right? We can develop this general formula that we can use, right? Tracing back to, okay, this 10 came from a choose function, right? So we'll introduce the choose function. And then we had the probability of success to the power of the number of successes times the probability of failure to the power of the number of failures, right? So we can develop this general formula. We can now develop the general formula for calculating the probability of K successes, for calculating the probability of K successes in N trials, we'll let lowercase p be the probability of success, with lowercase p probability of success. Now it gets a little hairy, right? But we're familiar with probability notation and we want to find the probability of k successes. So the probability, and here's where it gets a little bit new briefly. Let's clean that up. Is we use x just as a placeholder for the number of successes. X equals k. X is the number of successes that we're modeling. Oops. We could just write the probability of k, that's totally fine, but technically it's x equals k, is gonna be n choose k, right? So that choose function there. First, right? In our case, we had the 10, right? But in general, it's n choose k times p to the power of k, right? Where k is the number of successes that I'm interested in, times 1 minus p, that's the probability of failure, right? To the power of, if I have n trials and k of them are successes, then n minus k must be the number of failures. N minus k. It's good to get in the, or kind of get comfortable with replacing 1 minus p with q. Often I'll just replace it with q, where q is 1 minus p. So let q be 1 minus p, right? So q then is the probability of failure. So q is the probability of failure. I use q often, so it's good to kind of get in the habit, and it saves you the 1 minus p, it's just q. Right?
Why not use the complement?
Because it's the probability. You could, and it is, but we don't. How about that? You could, but we don't. Yeah, and I think it's because it's a probability as opposed to the actual event. Okay, good. So then we could write the probability that x equals k is going to be n choose k times p to the k times q to the n minus k. Notice that, of course, the powers here add to n, right? The number of successes plus the number of failures, right, have to add to n. Okay. So earlier, right, when we developed that formula, let's map this general formula back to what we established, right? And so earlier, we developed the probability that x equals 2, right? Which is exactly 2 successes was, we use that choose function, right? So we had 5 trials, so 5 choose 2. The probability of success was 0.2, and we were interested in 2 successes times 0.8 to the power of 3. I'll sneak that inside the bracket here. So you can do all these components individually, that's totally fine, but you need to be really careful that you're not rounding. Okay, so you want to keep all your decimal places until the very end. This one's safe because it's a finite number of decimal places, but later on we're going to have kind of long decimal places and super small decimals. So that's when it becomes really, really important that we're not rounding. Okay. So I'm going to say here, be careful not to round any values until the very end. Okay. So how I would do that, and like I said, you're welcome to go through each component and jot them down. But for me, I'm gonna just do it in one go in Desmos. So I'm gonna go back there. And I've already calculated the 5 choose 2. I'll go on a new line here. Now I want 5 choose 2, that stays the same. And just for practice, I'm gonna enter it again. So NCR 5, 2, bracket. And Desmos is clever enough, it doesn't need the multiplier if you're using brackets. So then I'm gonna use bracket 0.2 to the power of 2. And then notice how the cursor is up top here. So you want to step it down. You can just kind of tap it there. Just step it down. If you've used Maple, has anyone used Maple before? Yeah. Then you know you got to step it down. Otherwise, it stays up in the power, makes a real mess. Right. So then you can close that bracket. And it kind of just gives you a running answer, right, as you're adding things. So then times 0.8 to the power of 3. Oh, and sorry, I didn't mention it, but a to the power of b, if you want to use anything but to the power of 2, it's just a to the power of b button, and it puts you up top. And then you're going to step it down, close the bracket just to be fancy. And then that's the answer. All right. Bring this in. Oops. So now the probability of exactly 2 successes, oh, and maybe I'll crop this out too. Oops, is 0.2048. So the probability that x equals 2 is 0.2048. Right. So you could have solved that with a tree diagram. Sounds terrible, right? Don't do that, right? If you can convince yourself that you could solve it with a binomial distribution, although this formula, I know that this formula looks terrible right now, it's a lot better than having to draw out that tree, right? So let's kick it up a notch. What if I shoot 15 times, right? First, you're going to imagine your tree and tell yourself, I could do that, but I don't want to do that, right? So now, for example, if I shoot 15 times, what's the probability of exactly 2 going in? So if I shoot 15 times, what is the probability of exactly 2 going in. So I'm trying to get it in 15 times. So that's the number of trials that I have. So then n equals 15, right? So 15 trials. And I'm interested in 2 successes, exactly 2 successes. So k equals 2. I mean, it is the same probabilities as before. It's kind of a follow-up question, right? And so recall that P was 0.2 and Q is 1 minus P, so Q is 0.8. So now we can use this binomial formula, right, or this binomial probability formula to solve this, right? I always like to put out my empty formula and then I fill it in, right? So the probability that X equals K is N choose K times P to the K times Q to the N minus K. So now if I fill this in with the information that I have, right, I'm trying to find the probability that X equals 2, right? Which means that wherever I see a K, I'm going to replace it with a 2, right? And I'm looking at 15 trials now and 2 successes. Probability of success is 0.2 and 2 successes, and then 0.8 to the power of 13. Guess I should do 15 minus 2, but. So now I'm gonna just clean up that 15 minus 2. 15 choose 2 is 0.2 to the 2 times 0.8 to the 13, just to be proper. But you can go there immediately if you want. Okay, so now we can use our calculator, right? Kind of the new part of this is the 15 choose 2. So let's make sure we all get the same value. All right, I'm gonna clear this. And I'm gonna do 15, comma 2 is 105. So now I know that there are 105 different ways. So imagine your tree diagram, it's huge, right? You've got 15 layers. There's 105 ways that you could go down these branches and have exactly 2 successes. So let's see here. Let's keep going. I'm going to start using this answer button, which uses the previous answer. It's one of the ways that you can keep all your decimal places, right? And so what I'm going to do is I'm going to go on a new line, which is using this kind of blue enter button. And then if I hit this answer button here, it puts in the 105 from the previous line, which is kind of nice, right? I'm sure there's a way to store stuff, but it's been a while since I used Desmos, so I haven't used it since the last time I taught the binomial, probably last year. No, last spring. So I can't remember how to do that, but I do use this previous answer button a lot. And most calculators have a store function, right? If you're trying to keep all your decimal places, right? That might be nice to remember. But then what we wanted was times 0.2 to the power of 2. Step it down so you don't make a mess. Times 0.8 to the power of 13. step it down. Gonna bring that in. Right. This inserts the previous answer. So now I have the answer. I have the probability of exactly 2 successes in 15 trials now. And it can go here, right? Which equals, and maybe I'll go back to blue here, which equals 0.2308974418. If you had used a rounded value for 0.8 to the power of 13, right? If you were doing them component wise, this probability would be slightly different, right? So then when you go to enter your answer, it's going to be wrong. And so that's why I'm telling you, you have to keep all your decimal places until the very end, right? Then it might tell you round to 4 decimal places or something, right? But not until the very, very end. Okay. So that's the probability of exactly 2 going in 15 trials. Good. What if, kind of kick it up a notch here, I want to know the probability of at least 2 successes, right? So at least 2 of them go in out of 15. Okay. Really making you work for it. What is the probability of at least 2 successes in 15 trials? So now, at least 2 is going to include 2, right? It's one of those word problems where you're saying, okay, at least 2, but for us, at least 2 including 2, right? So this is 2, 3, 4, 5, 6, all the way up to 15 successes, right? I guess I should say or between here. Yes, okay, fine. 2 or 3 or 4 or 15 successes. Well, we just found the probability of 2. We could do the same thing for 3, same thing for 4, same thing for 5, 6, 7, 8, 9, 10, all the way up to 15. Still a lot of work, right? We're just making the calculator do it, but it's still pretty tedious, right? And so we're going to want to find another way, kind of a clever way of solving this, right? And so here, let's just make a note that we just found this probability. And we could do the same for the rest, right? For the rest, and then add them all up, right? because I'm saying or, right? 2 or 3 or 4 or 5. And then add those probabilities together. Right? Which would look like this. In terms of that probability notation that I introduced, right? What we're solving is the probability that X is greater than or equal to 2 is the probability that X equals 2 plus the probability that X equals 3 plus, and then all the way through to the probability that X equals 15. We're not going to do that. Why? We know the total probability of all the possible outcomes is 1 still, right? Probability, that's always true for probabilities, right? And so now, okay, so we could rewrite the probability of X being greater than or equal to 2. And I could say, well, what if I just took away all the options where it's less than 2, right? So not including 2, which is either 1 success, right? That's not at least 2, or don't forget about the 0 option. That one throws people off all the time, right? Even if I shoot 15 times, there is a probability that I get none of them in, right? So that's missing 15 times over, right? So we could say, or we could write the probability that X is greater than or equal to 2 is 1 minus the probability that X is less than 2. Which is a lot more reasonable, right? The probability that, so X is less than 2 is either 0 or 1 successes. So now all of a sudden I only need to use this formula twice instead of, I don't know, 13, 14 times, 2, 3, 5, whatever, up to 15. It's because this is included. Doesn't matter, right? A number of times, right? So now I could write this, I can rewrite this, and I could say, okay, how I'm going to solve this is I'm going to do the complement, right? At least 2, well, that's too much work. So then I'm going to say, okay, how about less than 2? And then I subtract it. So the probability that X equals 0 plus the probability that X equals 1, right? Don't forget about this option. Don't forget about 0. 0 factorial, no. 0 factorial is 1. Okay. So now I would probably go ahead and find these probabilities individually and then put it back together, right? Otherwise it makes kind of a mess. So we can solve the probability that X equals 0. Right, we're still using 15 trials, so it's 15 choose 0 times 0.2 to the power of 0 times 0.8 to the power of 15. I'll do that in Desmos. 15 choose 0, but I was going to say, what do you guys think it is? It's 1, right? There's only one branch down the tree where they're all failures, right? So then times 0.2 to the power of 0, still 1. So it's just hanging on 0.8 to the power of 15. paste that in here. So here, the probability is approximately, but I'll use an equal sign, 0.03518437209. And then we could do the same thing for x equals 1, but to kind of stay on track here, I'm going to do them on the same line, right? So now I've found that this value here can be replaced by this 0.03518, blah, 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 blah. So now I need to go ahead and add the probability that x equals 1. So now I'm going to use that previous answer button so that I keep all those decimal places. Plus, and again, n choose, so 15 choose 1, n bracket times 0.2. So now I have to have to the power of 1, I guess I'll show it, times 0.8 to the power of 14. Oops. Bring that in, right? The probability that x equals 1 is, oops, 15 choose 1 times 0.2 to the 1 times 0.8 to the 14. I don't have the answer, right? But that's this section here. So now I can find the probability that I'm after, right? The probability of having at least 2 is going to be 1 minus the sum, right? So the probability of at least 2, if I hit enter here, is 1 minus the previous answer. So here, this, the probability that x is greater than or equal to 2 is 0.8328742326, right? Keeping all your decimal places. So there's lots of kind of tricks to learn, right? But usually these questions are going to be in the format of, I make you do some calculations and then you use those calculations as a shortcut for the rest of them, right? I might make you find what's the probability of 0 or 1, and then I ask you what's the probability of at least 2, right? So for next day, what we're going to introduce is, what if we have, 200 trials, right? Then using this formula, if I want to know what's the probability of at least 50 successes, there's no easy way to solve that. So then we use the normal distribution. Kablam. But we'll save that for Thursday. If you have any questions, let me know. Otherwise, I'll see you then.